All right, today we look at something called L'Hopital's rule. L'Hopital's rule involves derivatives, but it's a way for us to figure out limits, okay? So some students start to get confused here because they start getting mixed up about what part of L'Hopital's rule is a derivative, what part is the limit, and then they start confusing it with earlier rules. Okay, so what we want to do here is realize exactly what L'Hopital's rule is. So L'Hopital's rule, if we look here, we've got the limit as x goes to a of f of x over g of x. So this could be a rational function, but this could be lots of other stuff. We could have an exponential function in the top, something logarithmic in the bottom, maybe something in the top that has both. It's partially polynomial, it's partially exponential, who knows, could be anything, right? But we've got a function on top, we've got a function on bottom. When we go to take the limit as x goes to a, we can't evaluate it. Remember, we always said we could evaluate limits where our functions are continuous by just evaluating the limit. But in this case, maybe we're having trouble figuring out algebraically what the limit actually is. Okay, so what L'Hopital's rule says is that we can use this tool where if we're having trouble with the limit algebraically of a function like this, what we can do is match that up, right, with the limit of the derivative of each of those functions. So we're going to rewrite this. Notice how our f became an f prime, our g became a g prime, right? So you take the derivative of the top, you take the derivative of the bottom, and then you check again. And if you still can't do it under the conditions we'll talk about in just a second, you repeat this process until it works, basically. So L'Hopital's rule works pretty nice most of the time. Sometimes you can get a really ugly problem, but usually it's pretty straightforward. So what happens is if you take the derivative of the top and the derivative of the bottom and you try to evaluate that limit, if we get a 0 over 0 condition, right? We call that the 0 over 0, or you get infinity over infinity, then basically it means that you should use L'Hopital's rule and evaluate the derivative again. Okay, so let's look at an example here. So see, I've got the limit as x goes to infinity of e to the x over x squared. So if we think about it, well, both of those functions are going to go to infinity as x goes to infinity. E to the x will shoot up to infinity, x squared will shoot up to infinity. So this is not helpful for us because we can't evaluate this limit directly, but we do have infinity over infinity indeterminate form. So that means we are now allowed to use L'Hopital's rule, right? You always have to check before you use L'Hopital's rule. Are you in 0 over 0 indeterminate form? Are you in infinity over infinity indeterminate form? And if you find one of the correct indeterminate forms, then you can go ahead and apply L'Hopital's rule. So what this means is we're going to take the derivative of the top function and the derivative of the bottom and look at the limit of that, and it will match up with the limit of this original function. So here we end up with the limit as x goes to infinity of e to the x over 2x. So you go, wait, only one thing looks different. Yeah, that's because the derivative of e to the x is e to the x. So the numerator didn't even change. But notice down here, the x squared became a 2x because we took the derivative. Now, obviously, if you didn't have an e to the x in the top, then this would be replaced with whatever the derivative of the numerator was. Okay, so then we've got this. Now we start thinking about, well, what's this going to do as x goes to infinity? Well, notice we are again in indeterminate infinity over infinity form. This goes to infinity, this goes to infinity. So we just keep repeating that process. So now I'm going to plug in, now I'm going to do L'Hopital's rule again. The derivative of e to the x is e to the x. The derivative of 2x is 2. So now it looks like we have a difference here, right? So as x goes to infinity, this e to the x is still shooting up towards infinity, but now the denominator is just 2. It's not going to infinity anymore, which means even if we wanted to, we don't have a reason to, but even if we wanted to apply L'Hopital's rule again, we can't do it because we're not matching one of those indeterminate forms. We have to make sure. So we don't fit the right indeterminate form now, but the good news is we can calculate our answer, right? So in this case, the limit as x goes to infinity of e to the x over 2, well, this will go to infinity. So now we know that the entire limit is equal to infinity. So it won't always be the case that when these two things go to infinity, that the whole function's going to go to infinity. The reason this one did was because e to the x was going to infinity or faster than x squared. But if we had this reversed where the denominator was blowing up faster than the numerator, then you can get a limit that goes to 0 or goes to all sorts of different values. So the key of how we did this, you apply L'Hopital's rule, which says take the derivative of the top, the derivative of the bottom, see if you're still in indeterminate form or if you can evaluate your limit, and you just keep repeating that process until you're done.